Okay, let's do some examples here so that you can see how we use the consolidation equation and its parameters to determine the consolidation settlement of a layer of soil in the field. Okay, so let's say that we have a site. And the site looks like this. Here's actually where the ground surface is, okay, and the water table is here, okay. And we're going to place a fill on top of this site. The site is underlain by low plasticity clay, okay. Gamma is equal to 20 kilonewtons per meter cubed. The clay is 6 meters in thickness, and the fill is 4 meters. It's not to scale, but you can see where I'm going there. And gamma for the fill is 15 kilonewtons per meters cubed. Okay, and the rock is down here. Now, because we're going to place a fill, which in this problem is a proposed fill, we haven't actually placed it yet. That is what these lines denote. It's proposed. Okay. Because there's going to be a fill placed on top of a layer of soil, we realize that this layer, which is saturated, is going to undergo consolidation, right? It's going to suffer the consolidation process, and therefore we would like to know what is the deformation that the layer will suffer, the consolidation settlement. Okay? Now clearly, when we place the fill, when we construct the fill, the layer will immediately begin consolidating. So what we are in search of is the ultimate consolidation settlement, which is the final and maximum settlement that is incurred by the clay layer due to the weight, in this case, of the fill. Okay, so we call this delta ultimate, also called delta at time equal infinity. Okay, the reason why we use infinity is to ensure that we have a subscript here that tells us that at this time consolidation has already finished. Okay, so we know that at time equal infinity, all processes associated to any engineering we do are going to be finished by that time, right? It's infinity. So this is just another way to write out the final, ultimate, maximum settlement, consolidation settlement of a layer when it is imposed a load. In this case, it's the fill. Okay, so that's the question for our problem. Now, what are we going to do? What do we do? Well, we need to realize that this is the layer that will consolidate, and therefore we're going to test a sample taken from this layer in the lab to determine the consolidation parameters. We're going to take, let's say that we're going to take just one sample, okay, to represent the whole layer. In that case, it would be reasonable to take the sample from the center of the layer, 3 meters below the ground surface. Okay, remember that this is the ground surface. This is a fill that we are proposing to place there. Okay, so we take that soil to the lab. When we test it in the consolidation test, it becomes now a specimen, because a specimen is basically a sample that is under testing. Okay, and from the lab we get the following parameters. Sigma p prime, the maximum stress that soil has ever felt, 250 kPa. E naught is 1.1, let's say. C sub C is 0.2, and C sub R, the slopes, the compressibilities, the inverse of the stiffness of the material in the first and second portions of the curve, the consolidation curve. These two parameters here are 0.2 and 0.03. Okay, so those are provided by the lab, let's say the lab that we hire to perform the test, or we could perform it ourselves if we are equipped with a lab. Okay, so here are the steps. Now it is important to say here that even though this will be a set of steps, okay, that we're going to write out here, it is important that you understand what is going on in every step. You cannot memorize the steps like a recipe, because then you will get into trouble if you don't understand what each step is. That is, later on, when we talk about consolidation part 2, this is consolidation, all this is consolidation part 1. When we talk about consolidation part 2, if you are not aware of what's going on mechanically with the soil at every point in time, in every step, you are going to get into trouble. So don't memorize this as a recipe that you don't have, you don't have any idea of what's going on. You just memorize steps. It's not the way to do it. In fact, of course, the reason why you are taking this course is to understand, not to memorize things. Okay. So the first step is to determine the stress that the particles are feeling at the time that is associated with no fill placement. So this is the time that we call time equals 0, where you are walking, let's say, walking around the site on the ground surface, and you're thinking about placing a fill on top. Okay, that's time equals 0. The effective stress there is also called the initial effective stress. That's another name, okay, for it. And this is equal to what? 3 meters of saturated soil minus 3 meters of water, the U. This is total stress, and then the U. Pore pressure is 3 times 9.81 kilonewtons per meter cubed. Okay, and so that is 30 kPa. Approximating this as 10. Okay, then we need to determine the final stress. What stress? Well, the stress that the particles will feel at this point at time equal infinity, because we are in search of the settlement at that time, at the end of, after the end of consolidation has occurred. So we call that the effective stress at time equal infinity. At that time, infinity, of course, the fill is already placed and the particles are carrying it. Not the water. The UE has already gone back to 0, right? The excess pore pressure has gone back to 0, and now the particles are carrying the fill. Okay? In this case, we have 4 meters of fill plus 3 meters of saturated clay, all right, minus 3 meters of water. And this is 60, right? 60, 30. So this is 60 plus 60, 120 minus 30, 9 kPa. Okay, so the initial stress that the soil is feeling at this point is 30, the particles, right? And then after we place the fill and the water takes the load, and then the water has excess pore pressure, and then the water seeps, the clay layer consolidates, deforms, etc. Then the particles are the ones that eventually carry that load, and the particles are feeling at that time 90 kPa. So the load, which is delta sigma, the load, which is delta sigma prime, is equal to sigma prime at the time in question minus sigma prime time equals 0, which is 90 minus 30, which is 60 kPa. That is the load, right? And that is, you can easily check, of course, this value, because the load is the whole fill, 4 times 15. That's 60 kPa, right? So we are good. Okay, at this time, what we do is determine, number 4, we determine the settlement by mapping the stresses. So what does that mean? This is what we're going to do. We're going to draw a plot here. We're going to put here sigma prime and E, and we're going to draw a generic consolidation curve like that. Okay? And we're going to map the stresses on this map here. What stresses? The ones that we just calculated. okay? Sorry, 30 and 90, initial and final, right? And also the pre-consolidation stress, which was provided by the lab, 250 kPa in this case. So 250, initial is 30, and final is 90. Okay? So the soil begins here, and it will end carrying 90. So we put these two dots here on the curve for the initial and final, and then we say, look, the soil is going to deform from a state of supporting 30 kPa as effective stress to a state where it's supporting 90 kPa of effective stress. And so the soil is going to deform along the first portion of the curve. Notice that this curve is, like we said before, made of two portions. The soil is going to deform along the first portion in our problem. Okay, so knowing this, we can now determine the equation, the nature of the equation that we're going to write to determine the settlement. Notice that the soil is going to suffer this reduction in void ratio as it consolidates from 30 kPa to 90 kPa. That's the void ratio that is going to, the reduction in void ratio that the soil is going to suffer, and that reduction, delta E, is directly related to the deformation that we are in search of, the settlement, okay? And the equation will capture that as well. So what is the equation? The equation looks like this. Settlement is equal to the slope of the portion we are concerned with. What is the slope of this portion? C sub r. 1 plus E naught H log sigma sigma. Okay, that's what the equation looks like. So notice that this equation is not precisely the equation of this portion of the curve, because if we were to write the equation for this portion of the curve, we would have the void ratio over here, right? We have converted the change in void ratio to settlement, so in the equation, by doing this fraction here, 1 over this, so that we can write out the equation so that we can get directly the settlement. Okay, so this is the equation that is relevant for us. That's the one we want. So what is it? Well, CR is given, it's 0.03, 1 plus 1.1, H. What's H? H is the thickness of the layer represented by the point that we took to the lab to test. Okay? So in our problem, if you look at it, this point is the specimen that we took to the lab, right, to determine the parameters. Here's the one we are using right now. And it represents a layer that is 6 meters in thickness. So this H is 6 meters. Log. Why log? Because this is a log scale. Remember, in a consolidation curve, a consolidation curve is plotted in an E versus sigma prime space, where the sigma prime axis is in log scale. Okay, like the grain size distribution scale for the diameter in log scale. So we need to then write out the equation so that it captures that. And so here's the log of sigmas. Here, what we have is the final sigma and the initial sigma. Okay, so the initial one is 30, we put it down here, and the final one is 90, we put it down here. Okay, so that's the equation. So numbers, and what you get here is, I have it calculated somewhere. Let's see. .04 meters. Why meters? Because this H is in meters. This has no units because it's a ratio, right? Each of them has units, kPa, but they cancel inside the ratio. This has no units, these have no units, this has units of meters. So you end up with units of meters here, and this is the same as saying 4 centimeters. Okay? And that's the answer for our problem. Now, let's say that when we are, we're doing this problem, we just finished it, and we're ready to tell the owner of the project or whatever that this is the settlement that we expect due to consolidation of the clay layer, right? We're ready to pick up the phone, and the phone rings, and it is the lab, okay? The lab people, and they say, hey, we made a mistake. We're sorry, we made a mistake. We looked at the data again, and the problem is that we wrote a typo. We had a typo in the report, and the sigma p prime is not 250. It's not 250. It's actually 75. Okay, so we're sorry. Please make sure that you realize that we made a mistake, and if you have to run any other analysis, please do so. Correct your analysis, and so that the sigma p prime, that is the correct one that you use, is 75. Okay. So at that point we say, okay, fine. We haven't called the owner yet to tell the owner what our result is for our analysis. So let's just do it again with the correct value, which is 75 kPa. Okay. So let's check everything. Okay, the lab provides now this corrected value. Everything else is the same. As far as they have told us, we don't have to change any other parameter. Okay, we determine the initial stress effective. That is the stress before we place the fill. Okay, the water table is there. Sorry, the water table is where we drew it, right there, right. And so the calculation is as follows: 3 meters of saturated clay minus 3 meters of water, which is U, that's 30. Okay, the final effective stress, that is the effective stress at time equal infinity after all processes have ended, including consolidation. It's 4 times 15, because now the ground surface is, it's 4 times 15 because now the ground surface is up here, right? That is at time equal infinity, the ground surface is there, not here. So we calculate our effective stress at that time, at time equal infinity, as 4 times 15 plus 3 times 20, okay, which is the 3 meters of saturated clay minus 3 meters of water. We get 90. That means that the load, which is the difference, is 60. Okay, so far so good. We keep going, map the stresses. The initial stress is 30, the final one is 90, and the maximum stress that the soil has ever felt, we said 250 was wrong, is 75. Okay, should we proceed? No, this looks weird here. 30, 90, 75, that's not the order. 75 should be here, so the break should be here. Okay, this is all messed up. Let's map the stresses again. Okay, we're going to do that in this page. So we're going to map the stresses. The correct value is 75. Okay, and the soil begins into the formation process under a stress of 30 kPa, and at the end of time, after consolidation has ended, the soil particles, of course, effective stress, are feeling 90. Okay, so now we are correct, 30, 75, 90. The break, of course, occurs at 75 because that is sigma p prime. So what do? Here we realize that the deformation of the soil occurs along both portions of the curve, from here to here and from here to here. So we need to write the equation out to capture that. The equation must capture both portions, not only the first portion as we did in the previous trial, okay, when we had the presumably wrong sigma p prime given by the lab. So here we write the equation. The equation has to have two portions. The first portion and the second portion. Okay? The first portion, the slope is C sub r, 1 plus E naught. The second portion, the slope is C sub c, 1 plus E naught. H, H. H doesn't change because H is the thickness of the clay layer, which we know from testing in the field, okay, that layer is 6 meters thick. Okay? Then log sigma over sigma, log sigma over sigma primes, right? Okay. C sub r, 0.03. 1 plus E naught is 1.1. This is 6. C sub c, 0.2. This is given by the lab, right? 1.1, 6, log. Okay, now, what are the sigmas? Well, we begin with the first portion. This part of the equation corresponds to the first portion. The deformation occurs from 30 to 75. 30 to 75 kPa. And the second portion, which has the slope C sub c, the deformation occurs from 75 to 90. So 75 to 90. Okay? And so there you go. You have everything completed there. It's just a matter of plugging the numbers into the calculator. Please realize that this is a log base 10. It's not a natural log. It's not ln, it's log. So use it accordingly. So what is the value? Well, hold on 1 second, let me calculate it. The answer, the value for delta C, delta infinity, right, is equal to 0.08 meters, which is to say 8 centimeters. Okay, that's the answer. So this is the correct answer, provided that we have a correct sigma p prime as given by the lab people. Okay, 75 kPa. Okay, so what you can do, of course, is take these two examples that we did. The first one with 250, okay, and the second one with 75 as sigma p prime. You can take it. You can take both of them. Of course, the idea is that you take both of them as two examples, two different examples. In one of which you use only the first portion of the equation, the first portion of the curve. Therefore, the equation just has the first portion part, okay? And in the second example, because the stresses are mapped in this format, with the sigma p prime in the middle of the deformation process, okay, then you end up using both portions of the equation, first portion and the second, okay? All right. Now, let's talk a little bit about what the book does. Okay, the book doesn't really go about explaining this in the way that I've done it here specifically. They use another way to have you determine what parts of the equation you need to use. Of course, they are correct, right? It's just an approach. This approach is as correct as the one in the book, but I believe that this approach that I teach with is a more clear one, because it really just shows you, what portion of what portions of the curve are going to be relevant to the deformation, and then how to essentially say that, okay, if there's both portions are associated to the deformation, then you write both portions of the equation. Okay, that's it's just as straightforward as that. I believe that's the most straightforward way, and that's why I teach it like this. Okay, but still, please read the book and make sure that you follow the way that they do it. If you don't have to study that way, this is the way that I'd like you to study, the one that I'm teaching. At the end, they are really the same. Okay. Now, I mentioned the book because the book, of course, uses the over-consolidation ratio concept to teach the student how to determine what part of the equations to use. That for one, and for second, it uses, for second, it uses the, it teaches the OCR as a concept that we should all know about, right? So the OCR is determined as follows. Let's use this example as a guide, okay? We said that before we place the fill, the soil at that point is filling 30 kPa, right? And then after we place the fill and the soil has consolidated, the particles fill 90 kPa. The maximum stress that the soil has ever felt is 75 kPa. So when we're standing at the site, when we're hanging out there at the site, not this one, sorry, where is it? When we're standing here at the site, wondering how we're going to construct this field, for example, the soil at this point is filling 30 kPa, but the maximum that it has ever felt is 75 kPa. So that point in the soil has felt a stress that is larger than the one that is feeling when we are walking around on top of the site. That means that some time ago there was maybe an event that moved, like a natural event, that placed soil on top of the ground surface that we know as the ground surface today, and then that soil got removed. So the soil was loaded to 75 kPa at this point, and then that soil got removed so that when we got to the site, the stress that it was feeling, the particles were feeling, was 30. Okay? Now, there could have been a structure here, an ancient structure or something, that was then destroyed or something, and then when we get to the site, you know, the stress felt at the point is lower than the maximum that it has ever felt. It is important to quantify that relationship between the stress at a point at a given time relative to the maximum stress that that point has ever felt, okay, meaning the particles' effective stress. So, in our case, for our example, 75 is the maximum and 30 is the stress at time equals 0. So, at time equals 0, we can describe this relationship between the stress at that time, the effective stress at that time, and the maximum effective stress felt by the particles in their life, okay, at that point, with what's called the over-consolidation ratio. Over-consolidation ratio means OCR is used to denote that. Most people just say OCR instead of, you know, the long over-consolidation ratio. So we're going to adopt that. We're going to say OCR. The OCR, in this case at time equals 0, is the pre-consolidation stress at time equals 0 divided by the stress at time equals 0. Okay? So, at time equals 0, that is the time that we associate with us parking the car and getting out of the car and just standing there at the site. Okay? There's nothing going on other than us getting to the site and wondering how we're going to construct the fill or what the structure is going to look like when we finish it, etc. So, at that time, the pre-consolidation stress, maximum stress ever felt by the point in question, 75 kPa, as provided by the lab. And the stress that the soil is feeling, the particles are feeling at that time, at that point, is 30 kPa. So that is the OCR, okay, for this time. If the OCR is larger than 1, like it is in this case, then we call the soil over-consolidated. Okay? So when you get out of the car at your site, you're standing there, you can compute this and you can say my soil is over consolidated. Okay? And that soil acts different than a soil that is normally consolidated, which is what we're going to talk about right now. What is the OCR at time equal infinity? Meaning, what is the OCR after consolidation has ended? Okay? That is the pre-consolidation stress, time equal infinity, divided by the effective stress at time equal infinity. So, time equal infinity, again, is the time associated with the end of consolidation or after. Okay? So, what is the maximum stress that the soil has ever felt? What is the maximum stress that the soil has ever felt if we ask that question at time equal infinity? Well, the maximum stress the soil has ever felt at time equal infinity is 90 kPa particles, right? So at time equal, it's no longer 75. 75 was the maximum stress that it had ever felt at time equals 0. But after consolidation is completed, the particles now carry the fill, and therefore the maximum stress that they have ever felt is what they're feeling, is 90. Okay? So this is 90. And what is the effective stress at time equal infinity? What is it that they're feeling at time equal infinity? Yes, they are feeling 90. So it so happens that at that time, the maximum stress that they have ever felt is the same as what they are feeling. So this is 1. This soil is called normally consolidated. Okay? A normally consolidated clay or silt acts different, behaves different than an over-consolidated clay or silt. Okay? Both in terms of deformation, in terms of strength, in terms of stiffness, etc. Okay? So our soil started from being over-consolidated before we placed the fill to normally consolidated after the consolidation process has finished due to the placement of the fill. Okay, let's do another example. We have a site. This is the profile, ground surface. Okay. So we have 2 layers. High plasticity clay with a unit weight of 20 kPa. Let's say this is 8 meters. Okay, and up here we have a poorly graded sand.